Alright, silly people, here's the situation. We're going to be solving the classic Wheatstone bridge, or at least a variation on it. And the first part of the problem is you see that you can get this equation for V1, treating V1 as your junction, um, and just saying V1 minus V plus over R1 gives you that, V1 minus 0 over R2 gives you that, then plus whatever current is coming from the diode, which is given by this guy, is equal to 0, right? The first part is to actually derive the corresponding equation using V2 as your junction, which, I've already done that. So that's this guy here. So it's V2 minus V plus over R3 because of this connection, and then V2 over R4 because of this connection, so this guy here, and then also the current which is coming from the diode, which is flipped to get the junction at V2, so you have V2 minus V1 here instead of V1 minus V2, right? But it's pretty much the same. Okay. The next part of the problem is to actually solve these systems of equations for V1 and V2 numerically, which it's kind of interesting because it involves calculating a Jacobian matrix, which is this guy. So you treat F1, you treat the first equation as F1, so V1 minus V plus stuff as F1, and then the second equation is V2, or F2, I mean, and then take the derivatives of the relevant elements, right? And so you get this Jacobian matrix if you do that, right? So getting the solution to V1 and V2 is pretty much a combination of solving the matrix which is or solving the linear equation which is formed by this matrix equaling the first two equations, and also Newton's method, right? So let's get into it. I'm going to go ahead and import NumPy as NP, and I'm also going to define all the constants. So we got V plus at 5 volts, we got R1 at 1 kilo ohm, we got R2 at 4 kilo ohms, R3 is 3 kilo ohms, and R4 is 2 kilo ohms. I0 is 3 nanoamps, so let me say 3e minus 9 amps, and I better make all these float values just to be sure. And then VT is 0.05 volts. Okay. Because V2 and V1 are going to be changing while you do your Newton's method, you want to make it so that both the two functions of V2 and V1 and also the matrix J are defined in functions, and then you call those functions to get the matrices that you're solving. So let me create a function which is called lowercase j, calling V1 and V2, right? And you're going to here define the matrix capital J, which is just this guy here. So let me type that up. NumPy array, brackets inside, and then brackets inside, and then make it float. Space this comma forward. First element, 1 over R1 plus 1 over R2 plus I0 times NumPy exp, in parentheses V1 minus V2 over VT over VT. Next element is minus I0 times NumPy exp, in parentheses V1 minus V2 over VT, capital VT over VT. Right. Next element down is minus I0 times NumPy exp, in parentheses v2 minus v1 over vt over vt. And then the last element, and I'm actually going to space this comma forward for prettiness purposes. Last element, 1 over r3 plus 1 over, I said hashtag instead of 3, it's kind of gross, r4 plus I0 times numpy exp in parentheses v2 minus v1 over vt over vt. Okay, and let me also space this bracket forward so we're nice. Then you can have that function return the array j. Cool. Next bit is to find the function of f. I'm actually going to call the function capital F of v1 and v2, and then have it return the list little f, and it is just a list where the first element is the first equation, so that was in parentheses v1 minus v plus over r1 plus v1 over r2 plus I0 times in parentheses numpy exp in parentheses v1 minus v2 over vt minus 1. Right. The second element is the second equation, so it's in parentheses. Actually, I'm just going to copy this element here because it's pretty much the same equation. Just replace v2 here, v3 here, v2 here, r4 here, and then v2 here and v1 here. Okay, so that's the function. We'll have it return little f. Now you can get into your Newton's method. Newman doesn't prescribe an accuracy for this problem, so I'm just going to go with 1e minus 4, and as always, create the error to be something that's really, really big. Of course, this time the error array is going to be, the error is going to be an array, right? Because we're solving linear equations. So while the error, or while the norm of the error is greater than the accuracy, then you can calculate the error, which is actually going to end up being a function call. So I should better define a guess that we're going to run through. I think a good guess that works is just setting v1 and v2 both to 0 to start out with. But once you get into the loop, you have to unpack it. So v1 equals x, 0, v2 will be x1, and then here you can make the error equal to the function f, called it v1, v2, divided by the Jacobian j, called it v1, v2, and then you take your guess and you subtract off the error, and then you print the solution. So this will run, hopefully. It did not. Non-broadcastable output operand with shape 2,2 doesn't match with 2,2,2. What you mean about that? Oh yeah, well it's because this isn't actually just one function over another. You have to, this is where you solve the linear equation. My bad, I was just autopiloting normal Newton's method. But then you have it solve j of, or little j of v1, v2 with big F of v1, v2. All right, that should make some more sense and should give us an actual result, which it does. So V1, we end up getting 2.66, and V2, you get 2. The way to check this is this part C says that the electronic engineer's rule of thumb for diodes is that the voltage across the diode is always about 0.6 volts. Well, the voltage across the diode will just end up being V2 minus V1, or actually V1 minus V2. So we'll take this number and then subtract off this number, and we get about 0.6. So I think we are right on the money for this one. All right.